print forms, which were extensively used, as you will see in the next two presentations. And the economy comes to a standstill in those sectors where we take people out of the production chain due to the lack of protection, and people are still at risk where they still have to work in the critical sectors. So robots offer great potential to be used in such crises, and here we give some examples of how robots are used in Belgium. And drones, who are quite available already, are calling, for example, with loudspeakers to keep social distance, or searching with heat cameras for people with fever. And a hospital in Geel employed corona killer robots that drives independently through the departments, armed with very strong UV lights, had to disinfect. And then we had also this smoothie robot from Alberts. It's a spring startup company founded by a researcher from our lab, which gives nursing staff their extra dose of vitamins every day over the smoothies. So it delivers touchless food. And also our unemployed Pepper robot from the AI Experience Centre was moved to a residential care center here in Hoelaert, where I live, with a telco app installed on the screen. And many elderly are feeling lonely, and due to the use of this robot Pepper, in a safe way, they can get in touch with family and friends. And the Belgian company Zora Robotics has even over 70 robots used in elderly homes. And then the Kingfisher robot from the biotech lab of VUB Prof Standaert was also taken away from his lab for analyzing COVID tests. But in contrast with computers, we don't have such robots widely available. So often there are just a few examples and they're not widely available. And of course, there is also a global effort to use robots against the fight against Corona. And here you see an overview of different sectors where robots are used currently to fight Corona. So they range from public safety, including quarantine enforcement, as in disinfecting public spaces, clinical care with, for example, healthcare worker telepresence, then for delivery, socializing, and telecommerce, then also for helping in labs as delivery and handling materials. And then you have the non-hospital care, as for example, I had a colleague professor who had to travel to a conference, had to go in quarantine, and in his hotel, his food was brought by a robot. But also after the Ebola outbreak, the White House Office of Science and Technology Policy and the National Science Foundation made an overview of how robots can make a difference, but because of lack of further finance and interest, those robots were not ready nowadays to fight this Corona crisis. And further robotization, which took place since the previous financial crisis, will I think now again gain momentum. And before, humans probably still preferred human touch instead of a robot. Hey, do you prefer a robot restaurant or food brought by a human? How do you like your coffee to be made? Do you want to be helped by a human when shopping or by a robot? And probably this will change in the future. And ideas that exist in labs and as demonstrators, as for example, cashierless shops, autonomous distributing of goods and food, robotic restaurants, further surveillance services, and so on, are now provided with an extra reason for existence, as I also wrote in a CNAC opinion piece. Important is to realize is that robots are still very inflexible. Why, for example, robots are not yet sewing our masks, and why we need to do it by hand in our cot. And because robots still lack the dexterity and flexibility that is required for such a complete new task. And therefore, the focus in our robotics lab is mostly on human-robot interaction in applications for health and manufacturing, as the development of cobots, exoskeletons, social robots, and prostheses. But if robots can replace people in crisis situations, why not afterwards? Digital surveillance can help bring such pandemics under control, but also threatens our privacy. Robots, as for example Spot, which is made by that famous company Boston Dynamics, are for example now used in Singapore to patrol in parks to measure, for example, that social distance, or robots that patrol airports and measure the temperature of travelers. As the famous historian and futurologist Harari wrote in the Financial Times, the Corona crisis will pass, but today's choices will determine tomorrow's life. And in the Homo Roboticus book we launched last year, we made 10 recommendations for an inclusive robot agenda. And the central question was how we keep the human values on solidarity, freedom, and equality stand ground in a robotized world. And the ethical values of a world with robots will be under additional pressure. And that is why there is an increased need for ethical vigilance. And no one will deny that speed of developments is of primary importance. And an important way to achieve this is with open source hardware. And the open source movement has already had a huge impact on information technology landscape. Think, for example, of Linux, for example. But also, for example, the use of open source microcontrollers and electronics like, for example, Arduino. But now there is also an increased interest in open source hardware. Because open source hardware is hardware whose design is made publicly available so that anyone can study, modify, distribute, make hardware based on that design. So users can more easily fabricate and improve on open source hardware without requiring large commitment in terms of cost, time, and domain expertise. And a relevant opinion piece was published in CNAC also by Jean-Claude Burgerman. He retired, he was responsible for open science policy of the European Commission, and he provided 4 important lessons for future science policy. First of all, he said that science matters. I think this crisis shows that it's more than ever the case. Secondly is collaboration. And also the 2 projects that we will discuss afterwards, will show that it was essential for bringing so fast a real solution from research to production. That typically takes much longer time to investigate and to manufacture. Therefore, he also made a stand for open science as a standard for science in the 21st century. Not hiding the developments, keeping them secret, but sharing knowledge to increase the speed of developments and avoid duplication of effort. And finally, also a red flag mechanism. It is not that researchers are today working in their ivory tower. There are a lot of science outreach events, and citizen science is becoming important, but still the voice of researchers is not always heard by policymakers. And he concluded that we cannot shut down the world again because we rather ignore science. So I want to conclude with my interventions with a quote of Steve Jobs: "The people who are crazy enough to think they can change the world are the ones who do." And I want to introduce Albert de Beir. He is an FAO researcher working under my supervision, and he is developing a genetic robot morphology tool for interactive evolutionary design, in which he includes human judgment to improve the appearance of social robots. But as the newsletter The Morgen wrote, he left his work as a robotics developer to enter the army of nerds and makers to fight Corona. And he's also an assistant in a mechatronics course, and he came with the idea to convert a Decathlon mask, snorkeling mask, into an emergency mask for the medical staff. And I think I never exchanged so many WhatsApp messages with researchers as Albert. It was a story of ups and downs, but I think with an impressive end result that due to the collaboration with several other partners and also industry, now all hospitals in Belgium could receive for free those masks and adapters, which also inspired the famous cartoonist Kroll to make this cartoon. So I think it's now up to Albert to say his story.
Okay. Do you hear me? Okay. So briefly, so the solution, most of you know it. The idea was really to use this kind of snorkeling mask to protect caregivers in hospital, especially at the beginning of the crisis, where there was not enough mask for everybody. So the end idea was really to 3D print a small adapter. It's very simple. You clip it on top of the mask, and you use a filter already widely available in hospital that you just connect, and then you transform this snorkeling mask in a protective mask for caregiver. So that was a 3D printed prototype for, let's say, 1.5 months ago, 2 months ago. And now we end up with this injection molded part, which has been distributed as of today to 40% of hospitals in Belgium, legally and with instruction, manual, and everything. And so what I'm going to tell you a bit today is how we came up with the idea and how many people around the world came up with the idea, and how you can come from this idea to prototyping to large scale. And there the answer is really collaboration. So how do you create this kind of collaboration? So first, really, the advantage of fast prototyping is you can go from an idea, a concept, you can improve it in a couple of hours. So the first prototype and idea were really a bit crazy looking, were not really practical. But when you want to look for a large-scale solution, you really need to take in account that first, you need to be able to scale it, and also it needs to be pragmatic. So it needs to be based on resource widely available. So that's how, from the beginning, I started to collaborate with Decathlon to check that there was enough mask for everybody, but also with the supplier of this filter material to make sure that they were widely available in hospital. Then you start looking for collaboration. So it's not about really making a 3D printed part. To give you an idea, between the first feedback I got from the doctor to this part I just showed you, took me a couple of hours. Then the 2 following months, it's been looking for collaboration, way to really push it, to find partners and to validate the solution. So the first part of the validation was to get feedback directly from hospital we knew we collaborate with already, to be sure that there was a need for this solution, and then to understand for who was the need. So what is the application, who's going to use it, how many times, in what type of situation. And that pretty rapidly, together with the hospital of Antwerp, we were able to really identify, okay, there was a specific need for this type of solution, and that's how they could be implemented. But then if you want to go large scale, and that's also very linked to liability, you need to make sure first that you can make this solution, that it works, but also you need to prove that it works. And that's really also a key point for this kind of project, especially if you want to go into a medical environment. And there, by having this kind of design open source, and there was also a lot of other research university that had similar project, that really helps finding new partners and create new collaboration. So mainly there it was with Stanford University and in Switzerland, the EPFL, that we were really able, okay, to team up as scientists and to share a bit this knowledge. And that's really where the open source is bringing a lot of value, because it's not me that has an IP and I send it physically, the device, and make NDA or thing like that. Someone could download the file, or I could download the files from someone else, print it in a couple of hours, do some testing, do some measurements. And that's how people all around the world, they could collaborate together to validate this solution. Then finally, once you do the validation, so you do a bunch of tests. For example, at the beginning, we were not sure whether this would provide a good fit, which means that it will be airtight. We were not sure that it could be disinfected easily and correctly. Also that it could be disinfected with the material that hospital already had available. And all these questions, so once they were answered, then the last step, which is sometimes I think the bottleneck right now, is to get that legally to hospital. And what I mean by that is that 3D printed parts, they are good, but you cannot do easily quality control. So there is a bunch of issues with this traditional fuse deposit modeling printer, mainly that the most used material, they don't support heating very well, so they will deform a bit if you try to sterilize them. You cannot really control and be sure you will always have the same part. And there is a lot of unknown about exactly what are the plastic, can they be used legally again in medical environment. And there the solution, especially if you want to go for large scale, was from the beginning to take in account, okay, we need a lot of these parts, let's go for injection molding. So this was one of the first part of injection molding. And that really simplifies also the amount of proof you need to bring to show the part is working. Because these are the same kind of plastic already used in medical environment. You don't need to prove that the concept is working and that the plastic is good. You just need to prove that the concept is working. And based on that, and then once we had the scientific validation, then we were able to find partners. So through Decathlon, I was put in contact with BIC. So BIC, you know, that is producing the BIC, or like the lighters. They can produce this kind of part massively, and they've been really part and really helpful on the project. And we've been able to create a huge consortium. And with this consortium, we could also push this very simple plastic part for let's say certification. So it's not a certification, it's a temporary authorization that we obtain in France. But because of that, I know it's only paperwork, but it's really important. If you want to say to the hospital, you can use my solution and you are not liable in something that works. It's not we showed it works, it's we have some authorization and we can provide it to hospital. And then really now with this kind of injection molding, in top of having a bit of better quality compared to traditional 3D printer, the main advantage is that you can mass produce large quantity, tens of thousands of units, and at a very low price. And you can have a quality control because, you know, with the mold, you will always get the same type of product. So as a quick summary, really, 3D printing was really useful at the beginning to share the idea so that when you have something, someone on the other side of the world can have it in a couple of hours and start testing. So it's really helped being fast and share this idea. But then 3D printing is not also a magic solution. And if there are no methods that work for large scale production, it's also important to consider it. Yeah, that's about it for me.
Okay, thank you very much, Albert, for this quick overview of how that project actually went. Part of and I think indeed your project mainly focused on how actually that production process get that right. If we now look at the project of Mark and Lieven and the Brussels Fab Lab, there were, I think, other complexities also involved. There are similar things. But I think it's interesting to see that also in the environment of the maker industry or the makers community, that there are also other challenges to be tackled when it comes, for example, to this ventilator project that Mark is going to tell us about. So Mark, please, the floor is yours.
Oops. Can you see my slides? I am still on mute, I think.
No, you're
okay.
you're
you can hear me. Yeah. Can you see the slides also?
Yeah. Yes, everything is fine.
Okay, there I go. So I'll quickly give an overview of our ventilator project. So I'm giving the talk on the left, and on the right there is Lieven Standaert, who actually managed most of the projects. So we have a website, the URL is given there, and basically, so what we set out to do is to build a ventilator toolbox, and the goal was to have it produce a fully functional medical ventilator. By fully functional, I mean it should do the same things that a conventional ventilator does, which implies, of course, accuracy, robustness, and reliability. And we wanted to do that as far as possible by sourcing components outside of the medical sectors. So that was basically the goal that we set out to achieve. Most of the work was done in our Fab Lab. So this is our university Fab Lab, of which you see a picture here while we were actually working on the ventilator project. So we started off on the 16th of March. We got a question from the Young Academy asking us, hey, there might be a shortage of ventilators in Belgium. Could you do something? And so we sat together and quickly we realized that we were indeed potentially capable of of making such a ventilator. To be honest, when we started, I think I gave ourselves maybe a 20% chance of success, because we had absolutely no medical experience, and even no experience with producing medical equipment. So I was quite, I can't say I was optimistic. I was enthusiastic, but perhaps not optimistic. And so a week later, we had our first working prototype. So going back, I think, to what Albert was saying earlier on, this would be the 3D printed phase. And indeed, a number of the components were 3D printed, but we also used quite a bit of laser cutting. And then, of course, you have to move from prototyping to production. And there we were really lucky to have a great collaboration with Audi in Brussels. And so by the 10th of April, we had 50 industrial, 50 units produced industrially at Audi Brussels. And so now, what we're doing now is testing for compliance. There is a British organization that regulates medical equipment, and they did us the great service of publishing requirements very, very soon. And so we went by those from the beginning. And so that's what we're doing now. And then, of course, the testing inevitably demonstrates that there are things that can be improved, or even shortcomings in our initial design. And so we're working on a version 2 right now. And so the starting point was designed by MIT, a low-cost ventilator. There was an old design, and then we used the specifications that Johns Hopkins in Baltimore had published. And then we, of course, the first thing, we went to our own university hospital for advice, because, as I said, we had absolutely no medical experience ourselves. So that's basically where we started. Now, what were the design principles? As I already said, it had to be a fully functional ventilator, and it had to be suitable for COVID-19 patients, because not every lung patient has the same kind of pathology. So there are particular things that you need to be aware of when you're thinking of COVID-19 patients. And for this, of course, we got help from our hospital. The machine had to be durable and reliable, and the criterion is roughly 600,000 cycles, which is like 2 weeks at a normal breathing rate. And so we wanted to avoid, also because we were not sure whether our project would be successful, we wanted to avoid adding pressure on the medical supply chain. So we actually used, as far as possible, other components, largely from the automotive industry. And we wanted it, after the prototyping phase, we wanted the ventilator to be mass producible, which would be like more than 100 units per day at a mid-size plant, such as, for instance, Audi Brussels. And we tried to make our toolbox, our design, as modular as possible, so that other people working with our project would be able to maybe take just a part of our toolbox and not the entire thing, and integrate that part into their project. So that was a design philosophy we had from the beginning. So what is the machine? It has basically 4 main modules. So it's a mechanical pump. If you can see my cursor here, this is driven by a windscreen wiper motor. And what it does, it actuates a plunger which compresses an ambu bag, which is a flexible bag which is used in first aid in hospitals. The mechanical parts are largely that should not say laser cut, that should say water jet cuts, aluminium sheets. We did water jet cutting mainly. Medical tubing and valves to the patient, that's all sourced from medical industry, because we couldn't avoid that. And it also, again, goes back to the liability issues that Albert talked about before. Then there's, of course, the control module, sensors, and that's an Arduino compatible microcontroller. And then, of course, the really important thing is that then the ICU nurse or the doctor gets some kind of familiar feedback, and that's I hope this is somewhat visible on the slide, but the big computer screen on the top right there is actually the kind of feedback which a ICU nurse would get, and which we designed to be identical actually to some conventional machines. So it's the kind of familiar feedback that you get, because of course if you don't have that, then your machine might be functional but not operable by the kind of staff that needs to operate these machines. So the team size varied between, at the sort of the heyday, we were 50 people working full time. Students were really crucial. There on the picture there, you see a number of our students working on designs and testing things. Alumni came, people who had actually finished their studies a few years ago. They came and helped us. There are a few staff members such as Lieven and myself. We got a lot of help from Flanders Make. They sent a few excellent R&D engineers that really helped us a lot. I told you about the hospital, and then we got a lot of help from companies, too much to actually go into here, but that was really instrumental. We could never have done it without the companies. Funding, so we needed a budget, so we Flanders Make stepped up and gave us 150,000 euros. We got a grant from the university, and then we also collected in collaboration with the VUB Foundation. They really helped us getting this off the ground, so we did a dedicated effort to get donations, and that gave us another 100,000 euros, which was much more than we ever hoped to get from a crowdfunding initiative. And this money is really important, because like the testing, not all tests we can do ourselves, and so it's really important that you get the adequate testing facilities, and that is not for free. So right, that's the testing we're doing now. As I said, we're using these British requirements for rapidly manufactured ventilator systems. We're doing as much in-house testing as we can. This is two of our colleagues from Flanders Make doing the tests in our lab. And then at a certain moment, you need to go to external testing, if only because you need a third-party witness. It's not enough that you test the things yourself and say that you're doing a good job. Someone else has to actually witness that you are doing a good job. Then, based on these tests, a new version is being designed and built, well, designed now and then built soon. We added oxygen. One of the tests, what we found, we did durability testing on the ambu bags. So these are these first aid bags that I showed in one of the graphs, in one of the slides before. It turns out they are not sufficiently durable. So we're moving towards a bellows solution, where we replace the ambu bag by a bellows that we made ourselves. And there are a number of other more incremental improvements in this version 2 of the ventilator. So I call this slide the business model, because it's sort of it's almost like business. We had to make a number of decisions on how we would position ourselves, actually. And so we really made a conscious decision not to become a producer of ventilators. Firstly, because this is not our core business. We're a university. We do research and development, but we're not a producer of medical equipment. And it would also have required a new entity, and we sort of I definitely was reluctant to step into such a new entity. So we chose to make the design available through the website that I already mentioned, and we also report on our tests and results through that website and in a number of scientific papers that are currently being prepared. And then, of course, we're there to help other teams who want to use the Breathny design, and that's already happening. We have collaborations with South Africa, Jordan, Canada, and a number of other countries. So we really got full legal support from our own university. I think this has really been a great help. And well, we'll see how we go along, but maybe we still need some kind of separate structure to actually house all this new expertise. Just about the cost, I think this is important. The machine in parts and assembly, excluding R&D costs, costs 2,500 euros. So the unit price of the machine is 2,500 euros, which you may compare to 20 or 50,000 euros for a conventional machine. So that, of course, begs the question: have we achieved something now in terms of effect on the market? And so that brings me actually to my last slide. What have we learned? What have we achieved? So I think one of the most important lessons that we learned is that as a Fab Lab, we can actually respond rapidly to a crisis. I don't think we actually realized it, but in a way, we had been preparing for something like this for at least 5 years. We had been preparing our own ability to react to a crisis by making sure that we had the equipment, that we had the team in place. And so this was really important. And our students, as I said, were key in this, as was the support from industry, which was, because of the crisis, of course, incredibly easy to obtain. It took us often 3 or 4 phone calls to get to the level of the CEO and to get a firm commitment the day after, which is probably not possible in normal circumstances. So that is one of my main questions that I at least still remain with, is how much of this experience that we have now is actually repeatable in more normal conditions. So then the second question that I'm asking myself is, given the fact that there will probably be no shortage in Belgium and probably nowhere in Europe, where can the machine be used? So this is actually a new question, is what countries are actually suitable markets, if I may use that word, for the machine, and how can we adapt to those, to make it useful to those countries? This is quite a difficult question, so it's not something you can just answer in one slide, but it's definitely what we are thinking about very hard now. And then, as I said, and that's then the final bullet of my presentation, is if we are able to make a much cheaper machine, we might have something comparable to what happened in 3D printing roughly 10 years ago. And they were also in the beginning very, very, very expensive. And then due to initiatives such as MakerBot and the open sourcing of a lot of these designs, the price went down drastically. And so I'm asking myself the question, and it truly is a question and not an answer: will we have our initiative and similar initiatives such as the event from MIT, will we have a similar effect on the market of ventilators by making these designs open source? So that's a question, and that's it from my side. Thanks.
Okay, Mark, thank you very much for this very crisp and transparent presentation of this adventure. I would say that you and your team have been made the past 10 weeks, and maybe to link to one of your learnings already. Maybe luckily that one of your findings was that we didn't need, or there was no shortage on masks. Of course, it's also due to the fact that we were maybe able to avoid situations that, of course, 10 weeks ago, or at the beginning in March and April, were not to predict, of course. And so to already nuance there a bit as well, of course. You already explained, and maybe before people can start dropping some questions in the chat box, I will maybe start first. You already give a little hint on where that the deployability or that this solution could be exported to, that there is interest in other countries like both in the Americas or in the Far East. Can you hint a little bit more on what the applicability, what they want to do there with the solution?
Yeah, yeah, definitely. So I think the first point is to identify the kind of countries that are both medically, you need hospitals and ICU units, and also in terms of production, you need facilities that can make this. And so what people are contacting us with is very much either from a research community, they want to take this design further, or actually, and this is for instance a case for South Africa, entrepreneurs that say, okay, your design looks good, it meets these requirements, I would like to build it as a company, and they of course even want to make money with it, which we discussed that, but we said, yeah, that's okay, why not? If you want to get it out there, someone will have to take a risk and build it, and so that's fine with us. So that's basically what's happening and what the other countries are expecting from us.
Yeah. And maybe to maybe drop another question then to Albert. I think that as you explained, Albert, in your project, of course, getting the right knowledge in to make sure that compliance towards the medical world. We're also, of course, the team of Mark maybe didn't have the experience in upfront and how to make sure that everything could be medically approved. I can imagine, Albert, for a researcher, jumping in this adventure on creating these adapters, your knowledge of materials and inputs of materials, and how it could be compliant towards the disinfection challenges and so forth. Where did you get your information from?
That's a very good question. So indeed, it was very a challenge, and I kind of want to say never again. So I did it for the crisis because there was a need. I think the knowledge, and that's a bit the beautiful thing, is that I learned everything from the community, the open source community. So when I'm saying this plastic can or cannot do it, is because all of this knowledge is shared, and that's really what's coming generally with the 3D printing world, is really this idea to share the knowledge. And that's what's really the advantage, is that you can move fast, and once someone has found something or have suitable information, you share it to everybody.
Okay. And did you, Albert, did you also had, Mark nicely put it under the umbrella of business model. So did you upfront, or do you already now have an idea on how to outsource it, or that yeah, indeed what the future will hold for this adapter?
So I will not call it either a business model, but there was at the beginning, okay, what is the need? And one of the first things we looked, as I say, it needed to be a pragmatic solution. And so it needed to be applied at least at the country level, which means that the first thing we look is that we say, okay, we have a solution based on these filters, are they available? And so it was also how to get this information. So we looked at for hospital, some of them had up to 10,000 units they were not using because it's used daily in daily operation, but all of this was canceled. So that was a bit, okay, what are the quantity needed? What are the people that want to use it? Based on these people, what is the quantity of masking like that? That also we check from the beginning with Decathlon, okay, can we apply it at a large scale? And then the second step was this: once you start to produce, then you need to have a clear idea of how much units you do. And then for sure, based on already all the data collected and knowledge we have, then it's also some information you provide to the sponsor. Because now the fact that this is offered for free to all hospitals is because we have ETIAS, which is you know, the big insurance company that is paying for the mask, and BIC that is developing and producing that for free. So you need to give them an idea of what are the quantity for Belgium, what is the need, and also you have all the logistics behind. How do you deliver that to hospital? How do you provide the information? How do you collect the feedback? Who can ask? And so all these questions, yeah, it's kind of a business model in a way.
Mm, yeah. In the meantime, an interesting question from Arthur de Krok came in for Mark. Indeed, what if indeed Mark was able to share us how that the funding for, of course, the period of the last couple of weeks, how did it actually developed, and that the question is there if there are people that invested in this open source project also now want to maybe have a stake in potential commercialization of the project. Maybe Mark, could you give a hint on that?
Yeah. So as I said in the chat, it is not really, in the sense that for many of the people that helped us, this was not actually their core business, and so it also shows that people have various different reasons to help you. Of course, there's always the ethical side. People really want to help because they want to help you. So I mean, there's nothing cynical about it. There's this true willingness to help. But then there's also what people find interesting for their own company. And for instance, for Audi, if I may speak for them, one of the things that was obviously very interesting for them was to demonstrate that they had flexible production, that they could switch from producing one thing to another. And so they, I think, are very happy that they were able to play this role, but they still see themselves as a car manufacturer, and they have no commercial interest in building ventilators. This might be somewhat different for the people who helped us with the PCBs, for instance. They have realized that they can do that they can make a different kind of equipment that they were not necessarily thinking of before. So they might, with us or without us, expand their activities in this field. But nobody has in any way limited our freedom to operate by saying, hey, we helped you, now we want a stake. So so in that sense, there's nobody actually said, if this becomes commercially viable, please give us a slice of the pie. That's a question we did. That's something we just did not hear at all.
Thank you.
Okay, maybe also maybe back to Bram Vanderborght. I think that what these two projects, of course, maybe also show to the broader audience is, of course, the added value of again becoming an engineer, which of course we all know that is always an added value for society. But does it also not prove that also at university level, and that's maybe to not everybody's knowledge, that the importance of having infrastructure, a Fab Lab, and have sufficient infrastructure available to have it integrated in the curriculum is even going to be more crucial in the future, to make sure that people like and master students and people like Albert, that these are people that really can go into a lean and fast design process, thinking ahead of these scalability issues and so forth, that is crucial in the curriculum process as well.
Yeah, I think our faculty places a very strong importance on the Fab Lab, and I think the Fab Lab is very new on the campus. It was before somewhere else in Anderlecht, but I think its importance only grows, and I think before the crisis it was already too small for all the students that could go there, and Mark is laughing, and I think afterwards, I think it will be even more important. So especially for industrial engineers, but also other engineers need to do projects there. And of course, now with this education from a distance over the computer, they cannot access the Fab Lab anymore, which is, I think, a pity, only the students that were involved in the projects. But for us, it's really important that students can go back to the labs and to the Fab Labs to also learn the practical skills. And at the moment, it also shows, I think, those two projects that a multidisciplinary approach from a project is very important. We do it already on a very strong way in our research project, as for example in BruBotics, which is a multidisciplinary team for developing robots, where they are the technical persons like engineers, AI people, and so on, but also the social, human, and medical persons. And we do already a lot of projects together. But this has to be pushed more also to on a student level, because you see, when you even make such a, I mean, it's crazy how much a piece of plastic creates so much headaches on a legal and medical field, that you need to collaborate with other fields, and they need to use their own strengths. And I think it's also a strength of the VUB, the famous team model of our rector that she always places, is that be excellent in your own field, but be reach out to other fields. So the T model, and I think those two projects especially show this, that it's needed, and that we further also need to be able to do that on an educational level, and place in the Fab Lab also other courses there. And that's also the reason, but maybe Mark can explain more, that already close to the Fab Lab is also the innovation lab from the Solvay Business School, had to bring the business side together with the engineers there.
Mm-hmm. Yeah. Maybe indeed also related to that, the last question that came in to wrap up the session is indeed, and maybe Mark, because you had a large team coming in the Process Fab Lab during this project, have you identified maybe also some shortcomings in the current curriculum while actually you've seen these students working on different solutions? So it was also maybe an opportunity there to see what skills that need further attention in potential update of the curriculum.
Yes, I'll give a truthful answer, which unfortunately is somewhat boring, but one of the things that we really discovered is the importance of documentation. If you want to make your initiative useful to others, you have to carefully document. And this is a skill. This is like clear writing and thinking and taking a step back about what you've just done. This is a skill that is not an easy one. And I think I became aware, I was super impressed by what my students could do. I was like very, very impressed. But I did see that there was in this documentation, there was something that they were not so good at, and that perhaps we should probably pay more attention to this aspect, because if you want to make open source stuff available to others, it has to be clear how they can use it.
All right, good. Thank you, Mark. Thank you, Albert. Thank you, Bram. Thank you for the audience to be present and to actually give us some questions as well. And I think it was very nice to hear some insights and some learnings from the three of you. Well, we're looking ahead for future involvements in both projects and of course in other things related to the activities of the three of you. So thank you very much for your time, and also for the audience, and hope to see you somewhere in the near future.
Thank you.
Bye-bye.
Bye-bye.
Everybody.